Voila! Well, you're on the light air now. So, welcome to episode number 83. And Eric literally just joined as I clicked on go live. So, that's it. We have, sorry for the time mix up. The US, for some reason, wanted to be the first to move to daylight time savings. So, next 2 weeks will be fun. But Ladislav and me had the date now, and yeah. So for those who are in US, you got an hour more to sleep, and now it's wake up for you. So anyway, well, let's just jump into it. Eric is here for fun and entertainment. Sorry.
3 heads are better than 2, right?
Yeah, and Ladislav is here to teach us something about fault tolerance, as far as I know. And for those who are here, well, before or after or first time, what we normally do is we go through the topic, and you can ask questions anytime in chat, and we will ask them, find a place in the conversation to have them, and yeah, then we kind of go from there for the next about an hour. Okay, so Ladislav, I'll let you introduce yourself, and you can go live if you want to.
Okay. So just in case anyone still doesn't know me, I live in Czech Republic. I like, obviously, as you can see behind me, a lot of good books, craft beer, and obviously programming. And at Red Hat, I contribute to SmallRye Fault Tolerance, obviously, which is what we're gonna talk about today. I also maintain Jandex. I'm committer at Microprofile and Jakarta CDI. And well, today, as I said, I'm gonna talk about fault tolerance, a little bit about how to write fault tolerant services, both in general and with Quarkus. All right, I have a little bit of a slide deck, so let me just share my screen and we'll go through that.
And you can just keep sharing your screen, then I'll turn it on or off as we go through. Yeah.
Okay, so I guess you see my screen now. It's just the 5 slides literally, so nothing terribly interesting. Before we get, I have a little bit of a demo that I want to spend most of the time in. But before we get to that, I wanna perhaps share 2 things. The first of them is this talk has like a little bit under 1 hour, so we obviously can't really get into any amount of detail. So I really recommend this book called Release It, published by the Pragmatic Programmers. I don't get any money from this promo. It really is that awesome. It's like a Bible of fault tolerance, though it actually is, as the subtitle shows, it's about designing and deploying production-ready software. The first edition was actually published in 2007 or so. So really, the topic of fault tolerance is much older than microservices and everything that's like hot today. The second edition is relatively recent. It doesn't have like useless craft such as JSP that you can find on a couple of places in the first edition. It's updated for cloud, microservices, and everything. So it really is.
So I don't have to read both. I don't have to read both. Just read the last one.
Yeah. The second edition is really good.
Cool.
So yeah. If you really have one thing to take from this presentation, it really be that this book is in your Amazon cart, right? The other thing I wanted to say is that, as you will see in the demo, the fault tolerance API is really a set of CDI interceptor binding annotations. Right? It's a CDI interceptor, but which like shows that you can apply it on like any method and basically use it as a glorified try catch, and that's a terrible idea. Right? I have seen often that people use it this way, and it really works best when applied to calling or to sending or receiving a request over network. Right? In any other situation, it will feel weird, and it will.
But maybe before we talk see the annotations and what is fault tolerance? What's fault tolerance in the context you are thinking about this?
Yeah, that's what
would be a very broad topic.
Yeah, that's what I was getting at.
Okay.
Really, you can use the API for like handling exceptions, but it's not designed for that thing. When it comes to it really is designed for calling and accept for networks for sending and accepting requests over network. That's where fault tolerance is like the first place where you need to think about failures, right? And you can like read on many kinds of failures, failure modes, and everything, but really the core is anytime like any all software projects these days and many years back do not live on their own. They talk with other services over network, and when that happens, obviously you will have services that are down. You need to be able to handle that situation. You will have services that are overloaded, and you will have to deal with that situation. You will have services that are clustered, fronted with a load balancer, and they will handle. They will sometimes feel snappy, feel all right, and other times they will feel bad. You will have to be able to cope with that situation. And so that's like the core set of things that you need to be prepared for. And that's like the core topic of fault tolerance.
Yes, for me, the way
that answers.
Well, I just said for me, the fault tolerance just means that how good your application is to handle failure in any part of the system, right? And fault tolerance, the API that we have in Mutiny is for a specific kind, right? It's when we call out to somewhere else, isn't it?
Right. Yeah.
You get other people too that think that fault tolerance is like an infrastructure concern and not an application concern, right? That, hey, if I deploy my app, Istio or something that's out there is going to protect my app from everything else. But in reality, especially in microservices, my challenge has always been if I'm working with a bunch of services, especially local development, the whole inner loop thing, if your app isn't fault tolerant, it makes that really hard.
Yeah. I think that's like, as I said, it's not just about microservices. Like many years back, applications don't live on their own. They call into other external services. Be it, I don't know, a validation of an address, right? That's typically something you offload to an external service provided by some authority. But that service itself may be down or overloaded. So yeah, being able to handle things that go wrong, or in completely other words, right? There's this saying that the distributed system is a system where a failure of a computer you didn't even know existed can affect your software. That's the world we all live in these days, and I believe that you can say it's been the world we live in for at least a decade or two.
Yeah.
I found too, like when I was in financial services, like when you got requirements as a developer from your Scrum Master or whatever, your stories, they never talked about how to handle when things went bad. They always talked about like, this is the right way to do it. But when you start getting into some of the stuff, it chases out these edge cases that you need to figure out what's the right thing to do when these things happen, because they're bound to happen, right?
Yeah. It's a the fancy term is a non-functional requirement, right? Obviously, performance is the prime example of non-functional requirements, but fault tolerance is in the same bucket, right? You need to be able to provide value, perhaps in a degraded fashion, even if other parts of the system or external systems exhibit failures, right? Yeah. Do we have like do we want to go more into these theoretical details, or I think we can just move to the demo?
No, let's go for the demo and what's
okay.
There.
Yeah, I think like what we've been talking about these past few minutes will be more clear on the following slide. Right, this is a simple domain that I figured could be useful for demoing what fault tolerance is and how to write and design fault tolerance systems. A caveat: I don't really know anything about stock management and portfolio management and anything, right? It's just the first thing I could come up with to show how a system looks like that has one part that you work on, but that has essential parts that someone else provides. Right. So in this case, the R system bucket is an application obviously written in Quarkus that will call into an external service that provides a current price of various stocks, right? And this application of ours will maintain a portfolio of stocks for each user, right? So what I have here is, and in terms of the demo, I have 3 Quarkus applications. The first one is the stock price service. The second one is the portfolio service. The portfolio calls into stock price. And the third application I have is users. That basically simulates a bunch of users, or you can say a bunch of web browsers open and looking at the portfolio service, right? And the users application calls into portfolio, right? And obviously, like the main question here at this point is, how does portfolio handle various kinds of failures of the stock price service? That is what will be focusing on. Maybe one more note. If you look at a diagram like this, you will start thinking about the boxes: users, portfolio, stock price. What are they doing? The interesting thing, though, are the arrows. That is like what the network calls are. And that is where fault tolerance obviously is the first thing, or like the arrows are the first thing you wanna think about when it comes to fault tolerance. Right. So I do have all these applications on GitHub. A link is at the end of this presentation. And what we'll do is use a lot of, like, all of the annotations from microprofile fault tolerance to make sure that portfolio stays alive and delivers a lot of and delivers value, its core value to the users, even though stock price is under various conditions. But that there can be many more failure conditions than I show today. But I think I'll show the most interesting ones. Right. So let me just start a few Quarkus applications. What I have here is I have the stock price service, which I'm gonna run. Maybe not. Oh yeah, I wanna do -jar. Right. So the stock price service listens on 50/50. Then I've got the portfolio service. I'll start it in dev mode because I'll be doing live changes to the code to improve its fault tolerance. That's what we'll be focusing on. Then I've got the user service, which I'm gonna start as well. That listens on 8080. Right, so let me just open a few websites. I've got all these services. Instead of in addition to like doing their thing, they also expose some statistics for the purpose of this demo. Right, so I've got the stock price service. I've got the 7070 is the portfolio service, and I've got the 8080 port, which is the user service. There are currently no users, so let me add a few. Right, and we'll see that the stock price service receives a lot of requests. But this graph shows how many requests it receives each second. Right, so it's roughly 70 requests each second at the moment. The portfolio service, this graph doesn't show requests to the portfolio service. It shows responses from the stock price service. Right, so it's got these two graphs, the stock price and portfolio graphs are complementary view on the same thing. Stock price the portfolio shows how many requests, how many responses we get, and the stock price shows how many requests it get. Right. So far it looks good, right? And here we see that each user has some stocks, its total value, and how long it took for the update to finish. Right. It's constantly hitting the portfolio service to show the current value. Again, as I said, I don't know anything about stock trading and portfolio management, and I think this is just, but I think it should be understandable for anyone as well. Right. So the first thing we can do, the first problem that can possibly happen is that the stock price service is down. I didn't even want to show this, but yeah, let's do that. I've got the stock price service here, and I shut it down, and users are getting errors. That's obviously not what you want, right? The portfolio service isn't getting any responses, and it's just propagating errors as it got them. So that's like it's nice that you can propagate an error fast, but that's not a nice user experience, right? So one thing I wanna show to just get rid of that is what I'm showing now is the piece of code that in the portfolio service that calls into the stock price service. This is where we'll spend all our time. So this get price method just uses the REST client to call into the external service, and if that call throws an exception, the method will just throw an exception. So what I'm doing here is, in case of a successful response, I'll put it into a cache, so that when the stock price service is away, I can just serve requests from the cache, serve responses from the cache. How do I do that? Well, I've got a method that falls back onto the cache, which can obviously be used with the fallback annotation. Right? I'll just configure a fallback method. Right, and right now, when the getPrice method throws an exception, that exception will be caught, and the getPrice fallback method will be used instead. Right, so I have the.
So the user has to keep the cache for himself first, right?
Yeah, that's right. The cache is populated kind of on successful requests. Right. So if I don't have any successful requests, the cache now is empty because I have the portfolio service running in dev mode. So it got reloaded, and right now the stock price service is away. So we're attempting to return everything from the cache. Obviously we have nothing in the cache, so I'm returning null to mean unknown value. Sorry, that's all. That's the best I can do right now. Right, so let me just bring the price service back just to show that that we can get some responses and cache some of the responses. Right, so we're getting some responses from the stock price, and the portfolio service just relays them back to the users. So, but right now I have like 20 entries in the cache out of 20 existing. So I have like everything in the cache.
Okay.
So
what's the green versus blue? Just
yeah, right. The green portion of the graph is when the response was served from the cache, and the blue one is the total.
Okay,
so there's
green means something happened badly and we recovered from it.
Yes.
Yeah. Okay.
Okay.
And blue means it's all normal. Okay. Yeah.
Yes. If I kill the stock price service now, we'll be getting responses from the cache again, right? So I'm all green again. But the users keep getting responses. They will become progressively more and more stale, right? But obviously in the real world, the cache would have a lifetime. But right here, just for simplicity, we'll just keep responding from the cache. Right. So that's like the first thing we can do. Let me just bring the stock price service back up again, because we're gonna see some more interesting failure scenarios. Right, so let me just a couple more users. Right, the stock price service I wrote in a way to simulate overload. Right, obviously in the real world, a service would be able to handle thousands and tens of thousands concurrent requests. In this demo, it's a little bit less, just to make it feasible. Right, so let's add a couple more users. Right, and the stock price service is getting more requests, but it's still, you see that there's one small drop down. And right here it shows that some errors start to happen. Right? The service becomes a little bit overloaded and becomes slow, and after becoming slow, it can even start responding with errors. Right? What I'm doing here is instead of like a real world service, I'm showing that what you can do is to have a mock service, if you can, if I may, that will show failures very early, so that you can actually prepare for those errors. Right. So here what we've got is there's so many concurrent requests that basically all of them are slow, and some of them even end up with an error. Right? So from what you can see here is that a lot of requests still get through to the stock price and return correctly, but some of them at the bottom will fail, and then the portfolio service will reply from a cache. Right, so we get, the users will still get their portfolio values, but sometimes they will get a little stale, and sometimes they will get slow. Right, at this moment, you can see that sometimes it even takes up to 5 seconds. Right, so let me add a few more users to show how it can get really catastrophic. Right, at this point, it will just a vast majority of the requests will slow will slow down and eventually fail with some kind of an error. And a vast majority of the users will get their response in a very, very long time. But in this case, it's 5 seconds, but let's pretend that 5 seconds is a lot. So the first thing you want to do is to guard the call to the stock price with a timeout. If it takes like 5 seconds and then ends with an error, it's basically useless to it, right? So what the first thing we can do is to add a timeout. By default, timeout annotation enforces a timeout of 1 second. So if I'll do that, the portfolio service restarts, and we see that all the requests take at most 1 second. Right? It often shows that I don't know what the real value is, but it shows that quickly, right? That's like if I don't know, basically the portfolio service restarted, so it doesn't know the values at the moment. But
okay, so the timeout means don't wait for this longer than that amount. Okay.
Yes, right. That's like as I said, one of the common non-functional requirements you have on a service is some kind is performance, right?
Yeah.
And obviously, response time is like there are two core performance metrics or requirements. That is like response time and throughput. And so here we ensure that the response time doesn't grow without bounds. That's like a useful thing to do.
Yep.
Right, but again, as we see here, a vast majority of the requests fail. Right, we can even see here that there's like 100 of concurrent requests, which this service is like designed to not be able to handle. Right, so in this situation, where you have a service, an external service that is failing a lot, the canonical solution that you will read almost everywhere is, well, you should use a circuit breaker. Right? I don't know how many of you know what a circuit breaker is. A circuit breaker is basically an automated fail-fast mechanism. It detects how many previous requests or previous actions failed, and if the number of failed actions is too big, then it will basically prevent any further calls to occur, and will throw an exception immediately. That's a very common way how to prevent the service on the other side to be overloaded. So let's add a circuit breaker. Portfolio service restarts, and what we'll see right here is that there will be a lot of spikes. Right, and between those spikes there will be pauses or breaks when no requests come into the stock price service. The pause, the break, that's when the circuit breaker prevents further requests to occur. Right.
So just because make sure you marked the client side, not client side, the portfolio side to be have a
yes, I have marked the portfolio client, the client to the stock price, to apply a circuit breaker policy.
Okay, so at some point the thing goes bad, it will back off and give it time to recover.
Yes.
Got it. Okay.
Yeah. Right. Don't keep flooding the network with things you know are going to fail.
Yes. Yeah. Right. As I said, it's an automated way of failing fast. And you could possibly have your own detection logic that could say, yeah, under these conditions, it doesn't make any sense to proceed, so let's fail fast. The circuit breaker does that automatically. With these conditions based on how many previous requests succeeded and failed.
And that's all within like a sliding configurable window, right? So it's based on a window look back of time that continually moves forward and advances.
Yes, exactly. But what you see here is you see the same thing here on the portfolio service, where most responses from the stock price fail, and so they or the circuit breaker prevented them from even happening, and that's where we respond from a cache. And so what we got here is that the responses are most of the time pretty fast, but sometimes they will be longer, up to 1 second because of the timeout. That's when a circuit breaker says, yeah, a long time or time enough has happened. Let's see if the service on the other side is healthy. I can't respond again. Right? That's how a circuit breaker will eventually return to a functioning state. If the service on the other side heals, then the circuit breaker eventually notices that. The problem here is that, as you can see here, the circuit breaker will notice that will prevent further calls from happening. The stock price service will heal down, and the circuit breaker will notice, yeah, this seems okay, and allows all the traffic to start again, which leads to immediate overload again, right? So circuit breaker is just a measure of last resort. What we need here actually is to be able to prevent overloading in a much more eager fashion. A very common pattern to do that is to apply concurrency limiting. Let's basically say that at most 10 requests may be happening concurrently. But if there's less than 10 requests happening right now, we can add another one, but if there's more, we'll fail. A concurrency limiter in microprofile fault tolerance is called the bulkhead. The bulkhead in general is a notion of compartmentalization or isolating failures, so that you handle a failure, or you have to stop propagating a failure in one part of the application, so that it doesn't affect another part of the system. A particularly common variant on this is limiting concurrency, or shrinking, or making sure that a thread pool, for example, is only of given size. So let me just add a bulkhead here, and let's see what happens. The portfolio service restarts, and it will eventually let all the requests through. Oh yeah, I know what's happening. This is not exactly
the bulkhead,
what I wanted.
but no retry, so the bulkheads just fail and don't.
Yeah, actually, the problem here is, and that's something that is a very interesting or maybe surprising way, maybe surprising part of the microprofile fault tolerance API. The fault tolerance strategies, the fallback, timeout, circuit breaker, bulkhead are nested in a way. And here, the bulkhead is inside the circuit breaker. So if a bulkhead prevents another request from happening, the circuit it will do that by throwing an exception. The circuit breaker will catch that exception and think, yeah, another failure happened. So what we have to do here, we could just comment out the circuit breaker or we can just say, yeah, in case a bulkhead prevented another invocation, that is not something we need to consider a failure. From circuit breaker perspective, yeah, let's just ignore that. Right? And what we can see right here, once that happens, you see that there will be very little concurrent requests, the bulkhead will prevent that. So some requests to the stock price service will fail due to the bulkhead, and those will be served from the cache. But as you can see on the portfolio graph, a majority of requests actually go through to the stock price. And since the stock price service is not overloaded, it can reply quickly. Right. So really what I wanted to show here, and users will get vast, like almost all the responses very quickly, and they will be a big part of them will be up to date. There will be some small amount of staleness there, but as we can see here on this graph, it will be a really small part will be stale. And I can add a few more users. Let me just add something like this. And we see that the stock price service can even handle, right now, it's something like 350 concurrent, not concurrent, 350 requests per second, as long as the concurrency is not too high. That is a pretty common behavior of a lot of network services, right? The concurrent amount of requests stays low, and the service is fine. Like as long as and when the number of concurrent requests grow, services very often go slow or start erroring right away.
So, so basically what you're doing is, instead of just the server trying to load balance or figure out by the client playing nice, things get better.
Yes.
Right. But we got a question from Yuan. It's just like when this runs in native mode, when compiled to native, does all this work?
Yes.
Yeah, and that's basically, so for Yuan, basically, if we ever do anything on Quarkus Insight that doesn't work in native, we will say so, but otherwise assume it will work in native. That is,
yeah. If anything if anything of this doesn't work in native, that's a bug.
Yeah. Very nice.
Right. So this is like one of the very common scenarios, and concurrency limiting, it really is a very nice way, a very nice thing to do, because it prevents overload. Now, obviously, what the stock price service should do and doesn't do at this point, it should be able itself to realize that, hey, I'm overloaded. Maybe I should start rejecting requests immediately. Right. And how would it do that? Well, there's a couple options. It could itself use a bulkhead. Right.
What, right? Which one could use what?
So let me repeat. What the stock price service should not let itself be overloaded. It should prevent overload, and it could do that simply by using a bulkhead too. Right? It's not just that the client should be nice to the service it calls. The service should also protect itself. Right? So the stock price service could use a bulkhead on its own entry point. Right?
Yeah, because that's what I'm realizing. This is not limited to anything, right? This can be done on any method. It doesn't matter if it's HTTP or gRPC or even just a normal.
Yes.
Any kind of method.
Yes.
Yeah.
Well, technically, no. It's a CDI, as I said, it's a CDI interceptor, so it can be used on any method of a CDI beam.
Sure.
Right.
So just curious, like, so what happens if I do a thread sleep 1,000,000 inside that method? Does this work? Does this handle it? It doesn't have to be a remote connection or anything. It just
Yeah. For example, if you sleep in a method that is annotated at timeout, there will be an interrupt. Right.
Okay.
Your sleep will get interrupted. That only works in case of synchronous methods.
Yeah.
In case you have an asynchronous method that returns a completion stage or a uni, there will obviously be no thread interrupt, because that would probably interrupt a completely incorrect thread.
Yeah.
But even in that case, the completion stage or the uni will complete after the timeout, even though the action is possibly still running. Right. Well, I'm using everything synchronous here just to make the exposition easier. But all this works on asynchronous methods as well.
Nice. Okay.
Right. Yeah. So there's one other thing I wanted to show, and that is like let me just stop all these for now. And I will just remove. So I've shown here like the 4 basic strategies that we have, which is fallback, timeout, circuit breaker, and bulkhead. There's one more which is called retry, and that I'm gonna show on a slightly different example. Right. So let's assume that the system looks somewhat differently. Right. We've seen that the stock price service can handle certain load comfortably, and then it will start crumbling and eventually failing. So if that service is ours, well, we can just say, why don't we spin up 2 instances of them of that, right? That should increase the capacity significantly. So what I do to show this is I have the REST client configured to point to localhost 5050. Let me just comment that out and instead use Stork. There was an episode on Stork some months ago, and let the REST client go to either localhost 5050 or 6060. Right, and for simplicity, I'll just use a round robin load balancing and a static discovery. If we were running in Kubernetes or anything with that discovery would happen differently. But that's just a detail of this demo set. Right. So let me just start 2 stock price services. I'll start the first one on port 5050, and I'll start another one on Quarkus HTTP port 6060. At this point, I have 2 services, stock price services running. I got one on 5050, and I'll open another one on 6060. Okay, just reset those. I'll start the portfolio service again in dev mode, and I'll start the user service again. Let's get back to the stock price service. I'll remove these annotations. I'll leave the fallback there, because we don't want to show errors. Right, so I've got the portfolio service running, the user service running. There are no users, so let me just add a few users. You'll see that both stock price services receive some amount of load. And the portfolio service here shows the sum of those 2. Right, so each stock price has something like 90 requests each second. So the portfolio has something like 180 responses each second, and everything works pretty well at this point, right? All users get responses pretty fast. I think at this point in time, the previous scenario already started crumbling. Let me add a few more. And in this scenario, it's still fine, right? Both stock price services are still very much in their comfortable space, right? This is what we wanted to achieve. But what I don't have right now is what happens if one of those stock price services goes down. Let me just kill one of those. And what we're getting here, some of the requests are happening from the cache. And the other service starts to get overloaded. Right, and a lot of responses here get pretty slow. Right, and I don't even have a retry here. Right, when the portfolio service tries to read a stock price from the service that's down, it will fail. The obvious thing I would do is, well, yeah, I should retry and hope that load balancer will redirect the call to the service that's live. Well, what would happen in that case? Well, let me do that. This one is down, and this one starts failing even more, right? Because it now has to handle the same load that was previously distributed across 2 instances, right? And that's like what I wanted to show here with retry, right? Beware of retry. It's almost never the right thing to do. It will lead to things like this, where eventually one of the services goes down and the other that would be just fine starts to will become overloaded, basically.
Because
Right,
basically,
so,
if your retry is 3, then now you're hammering that one 3 times as hard.
Yeah, by default, retries up to 3. I'll just limit that to at most 1. Right, but the service is still has to handle twice the load it was previously handling. It's still not gonna work properly. And what I can do, well, is do the same thing I did before. I'll add a bulkhead to the portfolio service, and the stock price service, and we still have only one of them. The other is still gone. The stock price service is now just fine. And so I just wanted to show that beware of retries. They are really like, you can shoot yourself in the foot very easily when you retry blindly. There are cases where retry is the right thing to do, but a lot of time you're just shooting yourself in the foot.
When would a retry make sense?
Oh, in my opinion, retry makes sense if you know that the service on the other side sometimes fails for no obvious reason, but you know that is not overcapacity. Yeah, right.
All right, sure.
In the situation where you know it's not overcapacity, it makes sense to retry, and you know that it sometimes fails because whatever, it's buggy, that happens. But in that case, I would retry that. Again, that really requires you knowing that the service is not overloaded.
Yeah. And otherwise, generally, it would be retry with some bulkhead or timeout or.
Yeah, definitely. Timeout should definitely be there for most of network calls, right? And bulkhead definitely, again, especially if you use blocking code, which is like very susceptible to becoming overloaded because of thread pools and everything. But then definitely in such case, a bulkhead should be put into place. But if you've got reactive services where one thread can handle 10,000 concurrent requests, that's a different scenario. But usually, even if in that reactive service, you've got some business logic to do, right? And that business logic will take time. So there will, even in reactive systems, there will be a capacity. So that you need to protect. Right? So even in that case, you really want to have a concurrency limiter. One thing that is rather unfortunate about the bulkhead here, especially about the bulkhead, is that it's configured statically. right? And this annotation by default says that there may be at most 10 concurrent requests. In today's world, where scaling, where elastic scaling can happen like instantaneously, it is hard to get a configuration of the bulkhead right. What we're planning to do and don't have yet is to create an adaptive bulkhead which will watch the requests and responses, and based on a ratio of failures and based on observed response time, will adjust itself dynamically. That's a known thing. Netflix has been doing that for years. So we really need to get this one added to SmallRye Fault Tolerance as well.
And you just remind me about this. So how does it actually play together with Stork and its load balancing thing? Does it just work, or is there anything to?
Yeah, that's just on the REST client level. But
Yeah.
the REST client here is configured to not use HTTP / localhost, but Stork /
Okay,
Stockprice,
yeah.
right? And the rest of it, the layers above it, don't know anything about stock being in place at all.
Okay, nice.
Right.
Yes, you do. You still. So yeah. So fault tolerance doesn't do load balancing. It literally just handles timeout,
Yes.
concurrency, that kind of thing. Whereas Stork is more about, oops, the thing is not there at all. Let's go somewhere else, or load balance, or spread the load. Yeah. Okay. Nice. Nice separation. Yeah.
I'd say one thing in my experience that I've seen here too is, like, I like the design you've got here where you've got something that's sitting on top of the REST client. I've seen people, and myself included, try to use like all the circuit breaker and fault tolerant stuff right on the REST client interface. And that just, you've got like multiple layers of proxying, and it just gets to be really messy really fast.
Yeah, you can do that. You can do that. You could add the bulkhead right here and everything. It would usually work, modulo problems. But in this case, I wanted to show that providing somewhat stale values is often a much better thing to do than write out fail. So I wanted a cache, and in this case, it's just a concurrent hash map in memory. It could be, I don't know, Infinispan or Redis or something like that. But just for simplicity, I've got a concurrent hash map. So I couldn't write this in the REST client interface, even if I wanted. So that's why I put it into an extra class. But in general, it is possible to write these fault tolerance annotations directly on the REST client interface. At the same time, it's also possible, like as we said, we can put those annotations on any method. So if I wanted the stock price service to guard itself, I would just go into the stock price resource. I've got a plain old Jexaris resource method. Actually using REST Easy Reactive, but it's still a Jexaris resource method. And I could put, and that's like the incoming piece of code that handles those requests from portfolio. And so if I wanted the stock price service to protect itself, I would just add a bulkhead here. Yeah, I wouldn't, because I don't have the extension. And so what I have here, so I could just add default tolerance extension, and then I could.
You're gonna tell Maven to rebuild your class path.
Yeah, I'm doing that. It's resolving them, and it should be done now. Yeah, I've got a bulkhead here, and I could add a timeout as well, or something. So yeah, you should have these concerns handled on both sides, right? It's typically like the most important places where you wanna guard against something bad happening is the network interface, right? The client that calls something over network, and the server which receives something from network, right? And on both those places, you want to handle problems, right?
Okay.
So yeah, I could put it here, right here on the stock price resource as well.
By the way, George is asking where the source code is for this demo. I think he likes the graph.
Yes, yes.
Guess. I don't know.
And the source code is in this GitHub repo.
That one. Okay. All right. If you just give them afterwards, we add to the description of the video after the call.
Okay.
Cool.
Right, and that's all I have. As I said, there's like a lot more that you could talk about when it comes to fault tolerance, but in case you're inclined, I really recommend the book. You released that book.
No,
we're using a bunch of the stuff in the sample app too.
Mm-hmm.
Oh, in the
superhero sample.
Yeah. Yes, sir.
Okay.
So
good to know.
No, I think that, well, maybe I'm just some of this stuff I always feel like when you read about it, always hard to actually do, but with this, it's just kind of trivial. It's a nice abstraction, so it's very good.
Yeah, there's one thing that's in progress. Like currently, you have to put those annotations on a method that you want to guard, or if you have multiple methods in the same class, then you can put those annotations on a class. But they can't be easily reused across multiple classes. So what we're currently working on is a programmatic API that would allow like centralizing fault tolerance configuration and applying that centralized configuration from multiple different places.
Okay, yeah, because I thought, yeah, like if you're calling a lot of services, how do you just make this generic thing?
Yeah, or even if you're calling multiple endpoints on one service, you will typically have multiple REST client interfaces. But you don't want to repeat all those annotations on each of those REST client interfaces, right?
For sure.
So in that situation, for example, you want to, like in this particular situation where you have two REST client interfaces, both pointing to the same server, you want to use the same bulkhead. You don't want to right? You don't want to say, yeah, for this endpoint, you may have 10 concurrent requests. For the other endpoint on the same service, you can do another 10 requests, right?
Yeah.
That wouldn't make any sense. That you would just keep overloading the service. You want to use the same bulkhead on both REST client interfaces.
Yeah.
So that's something what we're currently working on.
Cool. Okay. Well, we hit the 4 o'clock mark. Not many questions today, but otherwise, I'm sure we can be found on Sulip and on GitHub discussions for next time. And then I think, actually, this time I'm going to look at my calendar to make sure we're actually doing next Monday. Just to be, because I know we have something on Monday. Oh, no. Oh, next week is special. We have it's on a different day. And I don't have, that's on Wednesday. Yeah. So next week's Quarkus Insight is being a special because there's an event going on that we can't move around. So the next Quarkus Insights is next Wednesday, the 23rd at the same hour as usual. And that will be about Quarkus testing with Georges, I think, if I remember correctly. So yeah. So anyway, thank you, Ladislav, and thank you, Eric, for jumping in the last second. And we'll see you guys around.